Welcome to Review Lecture 3.3. Upon completing this, you should be able to describe a capacitor, calculate the capacitance of a parallel plate capacitor, calculate the effects of inserting a dielectric. Okay, now you may not realize it, but capacitors are everywhere. Every single electronic device you have probably has 1,000 capacitors in it. Electrical energy can be stored in a device called a capacitor. The computer memories use very tiny capacitors to store ones and zeros of binary code. Capacitors and photoflash units store larger amounts of energy slowly and release it rapidly during the flash. Enormous amounts of energy are stored in banks of capacitors, even ultracapacitors, that power giant lasers in the national laboratories or automobiles. So, in other words, capacitors are really cool. And all of these things are capacitors, believe it or not, including defibrillators. And they may even save your life someday. This is a capacitor too. That's in a camera. And there are capacitors in your keyboard, in the keys. So there's all kinds of capacitors are everywhere. Now, the simplest capacitor is any charged object. The simplest practical capacitor is a parallel plate capacitor. That is a pair of conducting plates separated by a small distance but not touching each other. Now, we've mentioned parallel plate capacitors in previous lectures. Now you're going to find out what they really are. The charges actually transfer from one plate to another by connecting it to a battery. Capacitor plates are connected to the battery's terminal, one plate to each terminal. The capacitor then charges as the battery moves negative charges from one plate to the other. The charging process is complete when the potential difference between the plates equals the potential difference between the battery terminals. That's called the battery voltage. The greater the battery voltage and the larger and closer the plates, the greater the charge that can be stored. The energy stored in a capacitor comes from the work done to charge it. The energy is in the form of the electric field between the plates. The electric fields are basically the storehouses of the energy in a capacitor. So in practice, the plates may be thin metallic foils separated by a thin sheet of paper or other material. This increases the capacitance and helps keep the closely spaced plates from touching and shorting out. This paper sandwich is then rolled up to save space and may be inserted in a cylinder. A charged capacitor will discharge when a conducting path is provided between the plates. Discharging a capacitor can be a painfully shocking experience if you happen to be in the conducting path. The energy transfer can actually be fatal where the voltages are high, such as in the power supplies of an old-fashioned TV set or old-fashioned amplifiers. Even if the set or the amplifiers have been turned off and disconnected from the power. Never touch the metal leads or wires of a capacitor unless you know what you're doing. Don't put your fingers inside of any of the old TV sets or any large amplifier. Don't do that. These are the leads here. These are capacitors. Never touch these. If you don't know what you're doing, these can literally knock you on your butt or worse. So don't do it. Don't touch these things. Don't reach into electronics you don't understand. Where does the energy stored in a capacitor come from? Well, it comes from the work done to charge it, because you never get something for nothing. Where is the energy stored in a capacitor? It's stored in the electric fields between the plates. Now, a capacitor will consist of two isolated conductors, the plates, with charges plus Q and minus Q. They're equal in magnitude, opposite in sign. The capacitance C is defined from C equals Q over V. And we have a new unit here called the farad, named for Michael Faraday. 1 farad is 1 coulomb per volt. Here's another one of those onesies I talked about. The V is the potential difference in volts between the plates. Q is the magnitude of the charge in coulombs on either one of the plates. Each plate has equal and opposite charge. So here's a picture of the two plates. Okay, and here is, of course, the electric field lines between the plates. Now, we usually ignore the fringing on the ends, and we just assume that all the field is between the plates and it's uniform. So we have a capacitor and a battery in a circuit. So here's the battery, here's the capacitor with its plates and a switch. So in figure A, a battery B, a switch S, and an uncharged capacitor C are, along with interconnecting wires, form a circuit. The same circuit is shown in the schematic diagram of figure B, in which the symbols for a battery, a switch, and a capacitor represent these devices. The battery's job is to maintain a potential difference between its terminals. The terminal of higher potential is labeled positive and is often called the positive terminal. The terminal of lower potential is labeled negative and is often called the negative terminal. Over time, the battery will transfer charge from one plate, that is a positive plate of the capacitor, to the other plate, which is the negative. This charges the capacitor. Now, you have to be careful with symbols. The battery symbol and the capacitor symbol look a lot alike, but they're not alike. If you are not careful when you draw circuits, you'll get these confused, then you're going to be really sorry. So the battery symbol is a pair of unequal length lines. The long line is the positive terminal. The short line is the negative one, sort of looks like a little negative sign. An ideal battery maintains a constant potential difference between its terminals while supplying current to the rest of the circuit. We'll talk more about batteries in a later lecture. Be careful to differentiate between the symbols for a battery and a capacitor. If you mix these up in your homework or on a test, you're going to be really confused. A capacitor has a symbol that is a pair of equal length lines, but there are other symbols for capacitors. A capacitor is used for the temporary storage of electrical energy and charge. An isolated ideal capacitor will keep its charge forever under all conditions, without leaking, breaking down, or shorting out. An ideal capacitor also does not have the fringing at the edges of the plate where there's a non-uniform electric field. We generally ignore fringing, leakage, breakdown, and shorting out. And unless they tell you otherwise in this class, it's an ideal capacitor. So here's a picture of a parallel plate capacitor. And by the way, the shape of the plates in this case doesn't matter for a parallel plate capacitor. It's just the area that counts. Plates are basically electrodes. So there are two electrodes, one with a charge of positive Q and one with a charge of negative Q. They're placed face to face a distance d apart. This arrangement of two electrodes charged equally and oppositely is called a parallel plate capacitor. So here is the edge view of this. So here's the positive plate, here's the negative plate, here's the electric field between the plates. You're looking down the capacitor between the plates. So shown as a uniform electric field of an ideal parallel plate capacitor constructed from two infinite charge plates. The ideal capacitor is a good approximation to a real one as long as the plate separation D is much smaller than the plate area A. And in most capacitors, that's quite true. The ideal capacitor's electric field is perfectly uniform between the plates and zero outside the plates. Ideal capacitors also do not leak, lose charge, break down, or short out. This is a real capacitor edge view. You're looking down between the plates. Outside the real capacitor, near its edges, the electric field is affected by a complicated but weak fringe field. Real capacitors also can leak, that is, lose charge over time, and can break down if overcharged or shorted out. In this class, we will assume the plates are very close together and use E equals sigma or epsilon naught for the magnitude of the field inside a parallel plate capacitor. This field is assumed to be approximately uniform. We also assume they do not leak, break down, or short out. Now shown are two capacitor plates seen from the edge. Connecting a battery to the capacitor's plate sucks electrons from one plate, that's a positive plate, and deposits them on the other, which is the negative plate. Because opposite charges attract and the plates are conductors, all the charges winds up on the inner faces of the two plates, so the surfaces that face each other. No charges on the outer surface. Inside the capacitor, this arrangement of charge means the net electric field points from the positive plate to the negative one. Outside of the capacitor, the net field cancels to zero, and it's assumed uniform between the plates. If little q equals big Q, which is the charge on one plate, and sigma equals Q over A, which is the charge per unit area, in other words, coulombs per square meter, that is the surface charge density, and A is the area of one plate. The electric field between the plates is the electric field of the capacitor equals Q over epsilon naught A, or equals sigma over epsilon naught, and it runs from the positive plate to the negative plate inside the capacitor, and it's zero outside the capacitor. Except at the edges, this field is uniform and constant in strength and direction at every point. A parallel plate capacitor is ideal for producing a uniform electric field, which is why I've been using it in examples of uniform electric fields. So here's a checkpoint. 3 points, 1, 2, and 3, inside a parallel plate capacitor are marked. Which of the following is true? Well, the electric field inside a parallel plate capacitor is uniform. Okay, we're assuming it's ideal. In which case, C is the correct answer. They'll all be the same because the field between the plates is uniform. Okay, here's an example. Calculate the charge of a parallel plate capacitor. Two 1 centimeter by 2 centimeter rectangular electrodes are 1 millimeter apart. What charge must be placed on each electron to create a uniform electric field of strength of 2 times 10 to the 6 newtons per coulomb? How much charge and how many electrons must be removed from one electron to the other to accomplish this? First thing you do is write down the knowns. And the important knowns, which is the area here, should be converted to SI units. So the area is 0.010 meters by 0.020 meters. We will not need the distance between the plates in this problem, but I just left it here. That's why I didn't bother converting it. The electric field is 2 times 10 to the 6 newtons per coulomb. We need to know the charge and the N, the number of electrons. The physics of this is a parallel plate capacitor. We're going to assume it has a uniform electric field. It's ideal. The formula E equals Q over epsilon naught A and Q equals NE. We solve for Q. Q equals epsilon naught A times E. So now we can stick in numbers. Here's our epsilon naught of 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. And the area is 0.010 meters times 0.020 meters. And the electric field is 2 times 10 to the 6 newtons per coulomb. The answer is 3.5 times 10 to the minus 9th coulombs, or 3.5 nanocoulombs. Now we want to know for the number of electrons that are involved. The number of electrons is Q over E, or epsilon naught A over E. The numbers then are 3.5 times 10 to the minus 9th coulombs, that's the charge, divided by the charge on one electron, which is 1.6 times 10 to the minus 19th coulombs per electron, and you wind up with 2.2 times 10 to the 10th electrons. Check the units. The units all look like they're okay. The plate spacing D does not enter the results. We're assuming that D is much less than the size of the plates, or in other words, the capacitor is ideal. If you are an algebra-based physics student, please skip ahead to slide 25. Otherwise, please stay right here. Okay, we're going to calculate the capacitance, and this is going to involve some calculus. So this is for Physics 222 students. This is for students who are calculus-based physics. And of course, non-calculus-based physics are not responsible for this. To relate the electric field E between the plates of a capacitor to the charge Q on either plate, we shall use Gauss's law, epsilon naught times the integral of E dot dA equals Q. The potential difference between the plates of capacitors is related to the field E by VF minus VI equals minus the integral from the initial to the final of E dot ds. We're going to let V represent the difference VF minus VI, and then we can recast the above equation as V equals the integral from the negative to the positive plate of E dot ds. The figure here shows a charged parallel plate capacitor. A Gaussian surface, right here, the little dotted line here, encloses the charge on the positive plate. We're going to take the integration along this path here from the negative plate to the positive plate. That's this little arrow, this green arrow that's pointing upward. We're going to assume that the plates of our parallel plate capacitor are so large and so close together that we can neglect any fringing of the field at the edges of the plates. We're going to take E to be uniform and constant throughout the region between the plates. The area of one plate equals A, the separation between the plates equals D. Epsilon naught is 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. We're going to draw the Gaussian surface such as it encloses just the charge on the positive plate. Then the charge equals, Q equals epsilon naught E times A. We use the electric field between the plates, and A is the area of the plates. V is then the integral from minus to plus of EDS. And that equals, we can pull the electric field out because it's constant. So E times the integral from 0 to D of ds, and that is just E times D. Now you notice, this is the same, this says that this field is uniform, V equals ED. Now if we substitute Q in the above relationships to Q equals CV, we get Q equals epsilon naught E times A. That equals CV, that equals C times E times D. So then C can be solved for. C equals epsilon naught A over D. Notice that C depends on the geometry, not on the charge or the potential difference. This is extremely important. The geometry determines the electrical characteristics of the capacitor, not the potential difference or the charge. So be very careful. There's a couple of trick questions in there. Now we're going to calculate the capacitance of a cylindrical capacitor. Again, this is Physics 222, or calculus-based physics. The figure shows in cross-section a cylindrical capacitor of length L formed by two coaxial symbols of radii A, the inner radius here, and radii B, which is the one that's to the outer cylinder. We're going to assume that the length of the cylinder is much bigger than the B, so L is much greater than B, so we can neglect the fringing of the electric field that occurs at the ends of the cylinder. Each plate contains a charge of magnitude Q. Here the charge and the field magnitude E are related as follows. Q equals epsilon naught E times A, or epsilon naught E times 2 pi RL. This is just the volume of the cylinder. We're going to solve for V. V equals the integral from negative to positive plate of EDS, and that equals minus Q divided by 2 pi epsilon naught L times the integral from B to A of dr over R, where R is the radius outward. V then equals Q over 2 pi epsilon naught L times the natural log of B over A by evaluating the integral. Now, if we substitute Q in the above relationships to C equals Q divided by V, we will get that C equals 2 pi epsilon naught times the length of the cylinder divided by the natural log of the outer radius divided by the inner radius. So C equals 2 pi epsilon naught L over the natural log of B over A. Notice that, again, the capacitance depends upon the geometry. The geometry of the capacitor determines the electrical characteristics of the capacitor. Now, this is a spherical capacitor, again, for calculus-based students. The figure shows in cross-section a spherical capacitor of two concentric spherical conductors, sort of one nested inside of the other, a radii A and B. So the little one is A, the inside one is A, and the outer one is B. Gauss's law for a sphere, Q equals epsilon naught E times A, or epsilon naught E times the quantity 4 pi r squared. Each plate contains a Gauss charge of magnitude Q. The electric field is E equals 1 over 4 pi epsilon naught times Q over r squared. We plug this expression into this expression for V and integrate. So V equals the integral from the negative to the positive plate of E ds. That equals minus Q divided by 4 pi epsilon naught times the integral from B to A of dr over r squared. Then V equals Q over 4 pi epsilon naught times the quantity 1 over A minus 1 over B. If we substitute Q in the above relationships from C equals Q over V, we will get the C equals 4 pi epsilon naught times AB over B minus A. Now notice again, the capacitance depends upon the geometry. So in other words, the geometry of the capacitor determines the electrical characteristics of the capacitor. Now, if you are a physics 122 students or algebra-based physics, this is where you rejoin us. Okay, so the capacitance of the three types of capacitors compared, and this is just a handy thing for everybody. Parallel plate capacitor, C equals epsilon naught A over D. A is the area of one plate, D is the separation between the plates. The cylindrical, C equals 2 pi epsilon naught L over the natural log of B over A. L is the length, A is the radius of the inner plate, B is the radius of the outer plate. Spherical, C equals 4 pi epsilon naught times AB over B minus A, where A is the radius of the inner plate, B is the radius of the outer plate. Now, in each case, capacitance depends only on the geometry, not Q or V. So this is like, we call capacitors electron buckets or charge buckets. That's one of the nicknames that electrical people have for capacitors. So it's like a bucket. The capacity of a bucket depends only on its geometry, not on the amount of water you put into it, which is analogous to Q, or how high you fill it, which is analogous to V. So remember that. There's a good test question in here. Okay, for Physics 222 students, calculus-based students, please stay here. If you are algebra-based, please go to the next slide, which is slide number 27. So the energy stored in a capacitor. Capacitors store their energy in an electric field between their plates. Now we're going to find an expression for this energy. There are several ways to do this, including calculus. The energy law says that the energy stored equals the work done to charge the capacitor, and you never get something for nothing. We're going to transfer a tiny increment of charge Q prime from one plate to the other. That will increase the potential of small amount V prime by doing an incremental amount of work. dW equals V prime dQ prime. Also, we know that V prime equals Q prime over C. Now, if you look here, this is a plot of the charge versus the voltage on a capacitor. And notice it's a linear curve. So in other words, and this slope is the capacitance, C. So the total work is then the integral of all the little work, and that will be 1 over C times the integral from 0 to cube of Q prime dQ. And that will equal Q squared over 2C. And that is the area under the QV curve, as expected. The energy U equals Q squared over 2C equals 1/2 CV squared equals 1/2 QV. That's taking various formulas and plugging them into each other. This is the energy stored in the electric field. And it's the energy stored in any electric field, by the way. Now, notice this. 1/2 times a constant times something, a variable squared. Remember 1/2 mv squared for kinetic energy? Whenever you see a 1/2 times a constant times a variable squared, it's probably an energy term. So when you see something like this, your brain should automatically say, click on something and say energy. It isn't always true, but most of the time it is. Okay, now if you're a Physics 122 student or algebra-based student, please start here. Capacitors will store their energy in an electric field between their plates. Now we're going to find an expression for this energy. There are several ways to do this, including calculus, which is the previous slide. But the easiest is to realize that the slope of the charge versus voltage curve equals the capacitance and is a constant for a typical capacitor. So C equals Q over V. Remember, slope is rise over run. So if you look at this chart, the slope of this is C. The energy law says the energy stored equals the work done to charge the capacitor, because you never get something for nothing. We're going to transfer a very small increment of charge, delta Q, from one plate to the other. That will increase the potential small amount, delta V. It will be doing an increment of work. So delta W equals delta Q, delta V. The total work will be the sum of all the little ones, and that will be equal to the triangular area under the curve OAB. And that happens to be 1/2 Q times V, so 1/2 BH. Also, Q equals CV. So we can plug these two things in and various other things and get various expressions for work. Work equals 1/2 CV squared, or equals 1/2 Q squared over C, or equals 1/2 QV. That is the energy stored in any electric field, by the way. So like many energy terms, it is 1/2 times a constant times a variable squared. Whenever you have see 1/2 times a constant times a variable squared, like for kinetic energy, 1/2 times mass times V squared. Most of the time, a formula like that says energy. So that should be sort of something floating in the back of your mind, so you recognize things like that. Now, the energy density of an electric field. Every electric field in a capacitor from any other source has an associated stored energy. In a parallel plate capacitor, the electric field is constant between the plates. Thus, the potential energy per unit volume, of course, the volume is the area of the plates times the separation between them, must also be uniform. The potential energy per unit volume is just called the energy density, and it's given the overused symbol little u. The little u is big U divided by A times D, and that equals CV squared over 2AD. We recall that C equals epsilon naught A divided by D, so little u is then 1/2 epsilon naught times the quantity V over D squared. From the discussion on electric potential, E equals minus delta V over delta S, or for a uniform field, V over D. In vacuum, the energy density U at any electric field of magnitude E is U equals 1/2 epsilon naught E squared. So there's 1/2 times something constant times a variable squared. The energy density units are joules per cubic meter. That is energy per volume. Now I'll narrate this while it's going. This came off the internet, and here's the guy who obviously did this. Kind of cool. So this is a parallel plate capacitor. He demonstrates various things about parallel plate capacitor. In a metal conductor, the positively charged particles are fixed in place, whereas the negatively charged particles, called electrons, are free to move around. A metal typically has an equal number of positively and negatively charged particles, making the metal as whole electrically neutral. If we apply a force trying to push extra electrons onto this metal plate, we will not be successful because the particles with the same charge repel one another. So in other words, they'll leave. So if extra electrons accumulate inside the metal plate, they will repel each other and repel any new electrons trying to enter. Therefore, even if we apply a force, the metal will remain electrically neutral. Now let us consider a new scenario where there's another metal plate close to the one that's shown. We'll show that in a minute. As electrons accumulate in the first metal plate, they will repel the electrons in the second metal plate. The positively charged particles left behind in the second plate will exert an attractive force on the negatively charged particles in the first metal plate. This makes it possible for the first plate to have more negative particles than positive particles. As we add electrons to the first metal plate, an equal number of electrons leave the second metal plate. After a certain number of extra electrons accumulate on the first plate, they will repel any new electrons trying to enter. The first metal plate has developed a net negative charge, and the second metal plate has developed an equal and opposite net positive charge. We can cause this equal and opposite charge on each plate to be larger by applying a larger external force. In other words, we're connecting a battery with higher voltage. If we remove the external force we are applying, the extra electrons in the first metal plate will continue to repel one another. We have now returned to our original condition where the net charge on each plate is 0. In other words, the capacitor has leaked down, has leaked off its charge. The two metal plates are what we call a capacitor. That's represented here. Note the voltage is shown upside down in this video because the blue arrows will show electron flow. This is a battery, a resistor. We'll talk more about this later. Here's the capacitor. Here's the electron flow. This is the voltage across the plates. By briefly connecting capacitor to batteries shown, the two plates have developed equal and opposite charges. After we charge up the capacitor, we will disconnect it from the battery. If we then connect the capacitor across the light bulb, all the extra electrons in the negatively charged plate will move to the positively charged plate through the light bulb. The light bulb will then light. The capacitor will discharge. And eventually the light bulb goes out. If we use multiple batteries in series, then we can force the two plates of capacitor to develop a larger amount of charge because voltages add in series. When the capacitor is charged, its voltage will be the sum of the voltages of all the batteries, provided they're connected in series. We'll talk more about that later. Charging the capacitor to a higher voltage will cause the light bulb to stay on longer and be brighter when the capacitor discharges. Now suppose that we increase the areas of the two metal plates. Make them larger. This increased area allows us to push more extra electrons onto the first metal plate and remove more electrons from the second metal plate without applying a larger external force. In other words, without a battery of a higher voltage. This is represented by a larger capacitor. When a larger capacitor is connected to the battery, it will take longer for the capacitor to charge the voltage of the battery, because it takes more time to store more charge. Although the final voltage is still equal to the voltage of the battery, for a larger capacitor, this voltage represents a larger amount of charge on the two metal plates. Now we connect our larger capacitor to our light bulb. The larger capacitor will take longer to discharge to the light bulb, thereby allowing the light bulb to stay on longer. Suppose that we add a special material between the two plates. This material does not allow any particles to flow through it, but contains molecules that change their orientation based on the charges between the two plates. These molecules exert forces that attract more electrons to the negative plate and that repel more electrons from the positive plate. The presence of this material has the exact same effect as does increasing the areas of the two metal plates. In other words, the capacitor can store more charge, and therefore is a larger capacitor, larger capacitance. This allows the two plates to develop a larger net charge for the same amount of applied voltage. When we increase the area of the two plates or add the special material, we say that we have increased the capacitance of the capacitor. There's also a third way to increase the capacitance of a capacitor. This is by moving the two plates closer together. Because the two plates are now closer together, they exert greater forces on each other's electrons. This attracts more electrons to the negative plate and repels more electrons from the positive plate, allowing the two plates to develop larger net charges for the same amount of applied voltage. This has the same effect as inserting the special material or as increasing the areas of the metal plate, so it makes the capacitance of the capacitor larger. To create the largest capacitance possible, we want to make the areas of the plate as large as possible, insert the special material between the plates, and move the two plates as close together as possible. The larger the capacitance, the more energy will be stored for the same amount of voltage. Now we'll go on. Capacitor with a dielectric. If the space between the plates of capacitor is completely filled with a dielectric material, the capacitance C in vacuum, or effectively in air, is multiplied by the material's dielectric constant kappa. That's a Greek letter kappa, which is a number always greater than or equal to 1. Now for vacuum between the plates, it's equal to 1. For anything else, it's greater than 1. In calculations, we would replace the permittivity constant epsilon naught with kappa epsilon naught. This is why you want to use the permittivity constant epsilon naught instead of Coulomb's constant K. Yes, I know, K, not kappa, K, which equals 1 over 4 pi epsilon naught. These are not the same. This is kappa and that's K for all calculations regarding capacitors or energy in electric fields. Placing a dielectric between the plates of a capacitor increases the capacitance by a factor of kappa. In 1837, Michael Faraday investigated what happens when a dielectric is inserted between the plates of a parallel plate capacitor so it completely fills the gap between the plates. And we will always assume that the dielectric completely fills the gap between the plates unless some problem states otherwise. He did this in two ways. What did he discover? The first way was this. He kept the battery connected to the capacitor. So the voltage remains constant because the battery remained connected to the capacitor as the dielectric slab, we call it a slab, was inserted. The plate charge increased from Q to Q prime, and Q prime equals kappa Q. The capacitance increased by a factor kappa. C prime equals Q prime over V, or kappa Q over V, or kappa C. The other way he did this was to charge up the capacitor and then disconnect it from the battery and isolate the capacitor, in which case the voltage across the plates would drop from V to V prime, which equals V over kappa. The electric field drops, E prime equals V prime over D, which equals V prime divided by kappa D, which equals E over kappa. The capacitance increases by a factor of kappa. C prime equals Q over V prime equals kappa Q divided by V equals kappa C. In this case, also in part B, the charge doesn't change. The amount of charge stays the same because the capacitor is isolated. So here's some dielectric constants and dielectric strengths. The dielectric constant is kappa. Kappa is always greater than or equal to 1. Kappa for a vacuum is by definition 1. Kappa for anything else is larger. So there's a trick question in here. Can kappa ever be less than 1? No. Kappa for the air is 1 to more than 3 significant figures, so we usually ignore the difference and set it to 1. The dielectric strength is also important. That is a breakdown potential. That is the electric field strength at which the material turns into a conductor. Remember I told you any insulator can turn into a conductor? So for example, potential difference of 3 times 10 to the 6th volts applied across the distance of 1 meter, which is a dielectric field strength of 3 times 10 to the 6 volts per meter, or 3 times 10 to the 6 newtons per coulomb, will cause the air to ionize into plasma and arc, or conduct electricity. That's equivalent to 20,000 volts per inch. So if you see an arc that's 1 inch long, that is 1 inch long, there's probably a potential difference across the ends of that arc of 20,000 volts. If you see an arc that is 1 meter long, there's probably a potential difference across the ends of that arc of 3 million volts. So dielectric strengths are important when designing capacitors and or insulation thickness. So there's sort of a safety factor when you design the thickness of the insulation on a wire. They take these into account. Capacitor with a dielectric with and without an applied electric field. Now these are for polar dielectrics, things like water, which is a polar dielectric. In other words, molecules with a permanent electric dipole moment. This was what happens before you put the electric field on. They're just randomly oriented. Okay, and they can be oriented any direction at all. That's what this means. So here's their little positive and negative dipoles. Okay, now when you apply an electric field, they tend to line up with the electric field. So this is the positive side of the electric field. So this will attract the negative parts of these dipoles. This is the negative part of the electric field that will attract the positive side. So what happens, the electric field is applied, produces partial alignment of the dipole. Now thermal agitation prevents the complete alignment typically. But these little molecules have an electric field, and you can see they kind of partially, this one is kind of attracted to the positive side. So you see that kind of partially cancels it. So it weakens the overall electric field. And that's what dipoles are, that's what dielectrics always do. They always weaken the overall electric field. Now here's a capacitor with a dielectric with and without an applied electric field. This is the atomic view for non-polar dielectrics. Those are the ones that do not have a permanent dipole moment. So here's the initial condition. There's no electric field outside here, and the little atoms in here are all perfectly symmetrical. The positive nuclei is centered inside their little electron clouds. Now, when you apply a field, it polarizes the dielectric and aligns the atomic dipole moment. So they have a little bit, here's the positive side, here's the negative side. So the electron clouds have a tendency to get tugged toward the positive side. The nuclei have a tendency to be more toward this side. The nuclei actually don't usually move. The electrons usually move more than the nuclei do, but they still end up with a charge separation. Okay, and you can kind of see what's going on here. This negative side will partially cancel that positive, and this positive partially cancels that negative. So what happens is applied field polarizes the dielectric, aligns the atomic dipole moments. The field of the aligned atoms is opposite the applied field. The overall effect, again, is to weaken the electric field by a factor equal to the dielectric constant. So E equals E naught, that's the original electric field, divided by kappa. So here's an example. If a capacitor has 4.2 times 10 to the minus 6 coulombs of charge on it, and an electric field of 2 kilovolts per millimeter is desired between the two plates, which are separated by 4 millimeters of air, what must each plate's area be? By what factor does this capacitance change if the dielectric constant 4 is used? So we write down our knowns. Knowns is Q equals 4.2 times 10 to the minus 6 coulombs. The electric field is 2.0 kilovolts per millimeter. And we're going to change that to 2 times 10 to the 6 volts per meter. The distance between the plates is 0.004 meters. We want to know the area of the plates. We're going to assume it's a parallel plate capacitor in air. Kappa is 1.0006. We're going to leave it in here just for the time being. Normally, we just assume it's 1. Okay, the formula is E equals V over D. C equals kappa epsilon naught. A over D, that equals Q divided by V. Also equals Q divided by D times E. And the D will cancel out of here. So in other words, you don't need to know the distance between the plates for this particular problem. The area equals Q divided by E kappa epsilon naught, and that will equal, the Q is 4.2 times 10 to the minus 6 coulombs. We're going to divide it by the electric field, which is 2 times 10 to the 6 volts per meter. The kappa is 1.0006 for air, and epsilon naught is 8.99 times 10 to the minus 12 coulomb squared per Newton meter squared. The answer to this is area equals 0.237 square meters. The capacitance will increase by a factor of C2 over C1 equals kappa 2 over kappa 1. That will be 4 divided by 1.006 or 3.9976. To all intents and purposes, that's 4. The difference between air and vacuum usually can be neglected. And unless they tell you otherwise, pretty much neglected. Checkpoint. Capacitor C1 is connected across a battery of 5 volts. An identical capacitor C2 is connected across a battery of 10 volts. Which one has the most charge? Well, charge is C times V. So C2 is going to have twice the charge of C1. What must be done to a capacitor in order to increase the amount of charge it can hold for a constant voltage? Well, it would be either 1, 2, or 5. Since Q equals CV, in order to increase the charge the capacitor can hold at a constant voltage, one has to increase its capacitance. Since the capacitance is given by C equals kappa epsilon naught A over D, that can be done by either increasing the area, decreasing the separation, or inserting a higher dielectric with a higher kappa. So be careful with these type of questions. Make sure you read all the questions. Whenever they do this, there's a trap in there, so be very careful. Read everything. Don't just pick the first thing you see. A parallel plate capacitor initially has a voltage of 400 volts and stays connected to a battery. If the plate spacing is now doubled, what happens? Here's possibly another trick question. Okay, both 3, the charge decreases by 1/2, and 7, the capacitance drops by 1/2. The battery stays connected, so V equals constant. Since C equals kappa epsilon naught A over D, when the spacing D is doubled, the capacitance C is halved. Since Q equals C times V, that means the charge must decrease by 1/2. Okay, if a parallel plate capacitor initially has a voltage of 400 volts and stays connected to the battery, if the dielectric kappa equals 2 is inserted in the capacitor, what happens? If it stays connected to the battery, the voltage will stay constant. So both 4, the charge increases by 2 times, the capacitance increases by 2 times. The battery stays connected, so the voltage equals constant. Since C equals kappa epsilon naught A over D, if kappa doubles, the capacitance doubles. V is constant, so Q equals C times V, so the charge doubles. A parallel plate capacitor initially has a potential difference of 400 volts and then is disconnected from the charging battery and isolated. If the plate spacing is now doubled, what is the new value of the voltage? Well, if it's disconnected from the charging battery, that means the charge will remain constant. So it'll end up being 800 volts. Once the battery is disconnected, Q has to remain constant, since no charge can flow either to or from the battery. Since C equals kappa epsilon naught A over D, when the spacing D is doubled, the capacitance C is halved. Since Q equals CV, that means the voltage must double. A parallel plate capacitor initially has a potential difference of 400 volts and then is disconnected from the charging battery and isolated. If a dielectric of kappa K equals 2 is inserted, what is V? It'll go to 200 volts. Inserting a kappa equals 2 dielectric makes the capacitance double. Since Q equals CV and Q is constant because the battery is disconnected, V falls to 1/2, so is now 200 volts. And 150 microfarad capacitors fully charged when it has 6.1 times 10 to the minus 3 coulombs charge on its plate. What is the potential difference across the plates of the capacitor? It ends up being 41 volts. Q equals CV, V equals Q over C. So 6.1 times 10 to the minus 3rd coulombs divided by 150 times 10 to the minus 6th farads, 41 volts. The plates of an isolated parallel plate capacitor with a capacitance C carry a charge Q. What is the capacitance of the capacitor if the charge is increased to 4Q? Okay, this is a trick question. The capacitance depends on the geometry, plate size, separation, configuration, and dielectric constant. It does not depend on the charge or potential. So the size of a bucket is set by the geometry of the bucket, not by the amount of water or the height of water in the bucket or the type of fluid that you stick in the bucket. Thank you.